My name's Aiden, and today I'm going to review a niche part of AP Bio. So, first it has to do with Hardy-Weinberg equilibrium. I'm assuming you're kind of at least somewhat familiar with this concept. So the first equation, P plus Q equals 1, is always true even if the population is not in equilibrium. This is because it is just assuming that there's two alleles. So the frequency of the first allele plus the frequency of the second allele has to equal the total frequency of every allele possible. So 100% of the alleles has to be one of these two. That's all it's saying. The second equation, though, cannot be used if the population is not in equilibrium because this is homozygous dominant, heterozygous, homozygous recessive. It assumes that each of these is equally likely to pass on their genes in reproduction, so on. It's assuming that none of these genotypes are selected for, which you don't know necessarily if it's not in equilibrium, which is why you can't use this if it's not in equilibrium. So how can you find these frequencies without if the population isn't in equilibrium? And this answer is actually quite simple. If you get the counts of each genotype, you can just count the number of alleles. So the first thing you need to know is that the number of alleles is just double the number of organisms because each organism has two alleles for that trait. So I'll go over an example right now. If you have, this table of all these different genotypes and the counts for each of them, the number you're trying to count up all the alleles. So the first one, homozygous dominant, has two dominant alleles, and there's 30 of them. So 30 times the two dominant alleles equals 60 total dominant alleles. Heterozygous, there's one dominant, one recessive. There's 30 organisms, so 30 dominant, 30 recessive. The next one, homozygous recessive, they have two recessive alleles, and there's 40 of them. So 40 times 2 recessive equals 80 recessive. And then what you can do, you just add all these up, and you get 90 dominant alleles and 110 recessive alleles. You can just calculate the frequency. The number of that type of allele divided by the total number of alleles equals the frequency of that type of allele. So P is for dominant, Q is for recessive, and these are the numbers you'd get for this example. So now I'm going to go over a very, very difficult MCQ question. This is probably the hardest possible AP Bio question you could ever get. I think I've only ever gotten one of them, the question is, in a very large population, a sample of 1,000 beetles are randomly selected. 150 are homozygous dominant for short legs, and 400 are homozygous recessive for long legs. Using a chi-square test at significance level p equals 0.05, determine whether there is evidence to suggest the population is evolving. So, part one of the solution, you need to just know the vocabulary. Evolving would mean that it's not in equilibrium. We're testing if it is evolving, meaning that our null hypothesis would be that it isn't evolving, meaning that it would be in HW equilibrium. So we don't know if it's in equilibrium, so we cannot use the second equation, and we have to calculate the frequencies by counting. So it gives us all the information we need to get these frequencies. You can just use my counting method exactly with this. It doesn't tell us the number of heterozygous, but we can just use subtraction because it tells us the number of total organisms and the number of each of these two types to find the number of heterozygous. You use counting and then you use division to find the frequencies of each allele, dominant, P and Q, right here. So the next thing you need to do is you need to use that second Hardy-Weinberg equation to see what the expected genotype frequencies would be if it was in equilibrium. So use these equations based on the actual P and Q numbers to find the expected numbers of each type if it was in equilibrium, and then you compare the observed numbers of each genotype, the ones that were given in the question, to these values in the chi-square test. So right here, you do a chi-square test, you put the observed and expected values here. The critical value for degrees of freedom of 2, because there's 3 categories, is 5.991. We see that our observed chi-square, our chi-square number is less than the critical value, so there is not sufficient evidence to say that the population is evolving. So we failed to reject the null hypothesis in this scenario. Thank you. Hope that helps.